This video will summarize what we did in class today. First of all, the whiteboard. If you want to copy that down, you can stop the recording and do that now. Next, we went to students giving the definitions for the Arrhenius acid and also for the Bronsted Lowry acid and base. Arrhenius acid and base. Okay? What I pointed out in class was that Arrhenius, with hydroxide ions defining a base, was in trouble. His hydrogen ions are okay because they're the same thing as a proton, but thinking of it very, very differently in the Bronsted Lowry definition. What's really different is how a base is defined. And the base for Arrhenius was just hydroxide ions, which did not explain why ammonia becomes a basic solution when it's bubbled into water. Okay, so this is actually what goes on, and the Bronsted Lowry definition of base as a proton acceptor just is perfect to explain that. And so what I did is I went ahead and wrote the equation for that, and then I defined it in the Bronsted Lowry way, which is the way you're going to be doing things in your homework tonight. So here it is, a Bronsted Lowry base, which is the ammonia, which makes their definition very different from Arrhenius. The ammonia is a base. It becomes a conjugate acid because it's going to take a hydrogen from the water. And because hydrogen is donating a proton or a hydrogen ion, both the same thing, then the NH3 becomes NH4. And we call this a conjugate acid, and over here we call this a conjugate base. Why? Because the proton was donated by the acid, and the acid became a conjugate base, which is what's left of the acid after it donates its hydrogen ion. Next thing we did was review this little sheet, which was in a video from yesterday, and also is available online as a printout that you could put right into your notebook, and this would go into Standard 5 because it's all acid-base. So basically, this has already been covered quite frankly, or quite completely, and we're moving on. So the next thing I did was to go through the practice problems and the other problems from last night. And that relates back to here, because this shows you exactly how to do each of these problems. So if you would like, you can go ahead and copy these down. Just stop the recording and do that now. And here are the answers, and you'll notice in both the answers for the last slide as well as for this slide, you see more than just the balanced equation. You will notice that we have here the sulfuric acid as aqueous because it's dissolved in water. Calcium is a metal, and all metals would wind up being solid except for mercury. And calcium sulfate would be aqueous because it will be dissolved in the water, and hydrogen will be the gas. So be sure you get down those little guys too. You need to be comfortable with those because they make a big difference in the stuff we're doing now. Next, I just showed this, a nice example of a base. Okay, when you're using soap, you're using something that's slippery, and slippery is equivalent to base. And what makes it slippery? This guy, right here, hydroxide ions, typical of bases. Okay, whenever you have a basic solution, you are going to have the hydroxide ions, and that's what the slippery is. Here are just some graphics that I found online. You can find them online yourself, and these were just used as examples to show of what we would have found yesterday when we were looking for examples of acids and bases. And here we've got lots of different acids: wine, vinegar, bufferin, limes, lemons, and any citrus fruit. So that's that guy. This is showing both acids and bases that are common in everything that we work with. Uh, the baking powder is acidic, and vitamin C is acidic. Lemon juice, of course, is citrus, so that's acidic. And here we have our vinegar again. And over here we have an ammonia cleaner, oven cleaner, very strong base. You wouldn't want to use acid. You'd want to use base. And Drano, really powerful stuff. And baking soda becomes a base as well. So nice little common household stuff. And over here we have lots of bases. Drano, Schweppes, which is just mostly carbonated water. And here's a heavy-duty oven cleaner, Tums for your tummy, and baking soda again. So lots of nice graphics that you can find on the internet to show you about common household stuff that's either acid or base. Now I'd like you to watch this little animation that I showed in class. Watch it once. There. Now you need to see what's happening. See, this is the proton that came off. He left behind the electron. And so over here we have the acid. Over here the conjugate base, which is the acid, with the proton, the proton is gone. And the base is the proton acceptor, and you see the base on the other side is called the conjugate acid. Because if the reaction goes back to the left, you're going to get acid and base. Actually, now these would be called the base, and these would be called the acid because they're on the other side. So this guy's in equilibrium. Let's watch this guy one more time. And by the way, you can get this guy right on my website on today's, which is May 9 of 2014. There's a link for this little animation. It was done by a student of mine about 7 years ago. Okay? So you've just seen it again. You can watch it as much as you want. This page you need to copy down. So stop the recording and copy this down word for word. You want this in your notes because it will help you a bunch. It not only has the definitions of acid and base, according to Bronsted Lowry, and the definition of a conjugate base and a conjugate acid. So stop the recording now and copy this down. Okay, here we go. Let's get this cleaned up. This little guy is given to you actually in your textbook, and you will find that on page 599 of your textbook at home. And this little graphic is right at the top of the page, and it goes along with this particular reaction very nicely. So if you look at that and compare, you'll see what's going on graphically, which is very, very nice. Now I'm going to kind of get that out of the way, and let's go ahead and label these guys. Okay, our acid is the hydrofluoric acid, and this guy is going to become the conjugate base. The way it does that is it's simply going to give away the hydrogen ion. And when the hydrogen ion is given away, it's going over to the water, and this guy is going to become our conjugate base. Okay? Now, when we do the water is acting as a base, and so that guy we'll label as our base, and the base now is going to become a conjugate acid by coming over here and losing. Boy, I messed this up really good. We've got to get this fixed. Okay, I messed this up really bad. Okay, I've got the acid and base fine, but I went to the wrong conjugate. So, starting all over again, we're going to have the acid become the conjugate base. The conjugate base is over here as the fluoride. Okay? And so the fluoride is actually going to be our conjugate, not our conjugate base. This guy's the conjugate acid. There we go. Now I got it right. And this guy is our conjugate base. And so the conjugate base now is what the hydrogen ion was before it lost its proton. So now that I have that all fixed up, it looks right. So let's trace it with the arrow here. Here's our acid. The acid is going to donate this hydrogen ion, and the hydrogen ion is going to the water, which will look like this on the other side. So water, who is the base, becomes a conjugate acid when it accepts the proton that came from the hydrofluoric acid. The base, which is the water, accepts that proton, okay? When this proton leaves the fluoride, he becomes the conjugate base. And the conjugate base now is the acid without the hydrogen ion. And that's how that guy works. Let's go on, and we'll just do another quick thing here. Let's go to the next page, and we're going to do the same thing all over again, only this is the same reaction. I don't know if you noticed that. Let's go back and do these guys side by side, and I think that'll help. Okay, so let's get this little dude out of the way a little bit, and we'll get this guy down. And now let's go ahead and do the same thing on this side. In fact, why don't you do this on your own? Stop the recording, see if you can label the guys on the right. I hope you stopped it and had the opportunity to learn something, because now this guy, the water, which is what we call amphoteric, amphoteric meaning it can be an acid or a base. You see on this side, he is now called the acid. Why is he the acid? For one reason and one reason only, because he is written on the left side of the equation. You notice we're going to have conjugate bases on the right side, and what was an acid is going to become a conjugate base, and vice versa. So here we go. It's going to become a conjugate acid. There we go. Now, our acid and our base. We're right on track here. So the acid now is going to donate his proton, and that proton is getting donated to the fluoride ion, and so the fluoride ion now becomes the conjugate. Oops, it's going to be donated. My goodness, I missed it again. Shame on me. It's going to become the conjugate base. Bases are bases and acids are acids. So the acid becoming the conjugate base, and the base becoming the conjugate acid. And let's change the color on that. I just grabbed the wrong pen. And now we've got our conjugate acid. So notice what was the conjugate acid in the right-hand screen is the acid on the left-hand screen. What's the conjugate base on the right-hand screen? Look over there, and what do you see? It's the base. So bases are bases, acids are acids. The only difference between the base and the acid and the conjugate acid and the base and the conjugate base is that the base and the acid are on the left side of the equation. The conjugate acid, conjugate base are on the right side. And that's it for today. I hope you find this helpful.